Okay, we can start. Good afternoon, everyone, and welcome to today's lecture by Dr. Dharmapriya from University of Peradeniya, Sri Lanka. He is a non-metamorphic petrologist in Sri Lanka, and his major research focus on high-temperature metamorphic rocks and its tectonic significance. And today, he will be talking about the geological origin of gemstones associated with both metamorphic and igneous rocks. So I welcome him to this lecture series, and Dharmapriya, please carry on.
Thank you very much, Dr. Atira, for your kind introduction. So I think during next 1 hour, 1.5 hours, we are going to discuss about gemstone. So not only geologists or person who are engaging with earth science. So everybody actually they prefer to engage with the gemstone because today, sorry. Under this particular title, I'm going to, so this is the main content. So at the very beginning, I will briefly introduce what are gemstones. So after that, by these gemstone, when you are considering gemstone, these are very rare materials. So what are the reasons for that? Why are gemstone rare? We will discuss some more information regarding that. And after that, geological origin of gemstone, because nowadays people produce synthetic gems in laboratory scale after producing artificial conditions. But here, I mainly focus on the naturally occurring, natural formation of gemstones. So under that, actually, there are different mechanisms through that gemstones can result naturally, but due to the limited time constraint, I mainly focus on some examples related to igneous origins and metamorphic origin. So first, what are gemstones? So gemstones are actually majority of gemstone, they represent minerals. So minerals mean we must know to define a material as a mineral, the particular material or the substance should fulfill 5 factors. It's a naturally occurring substance, and also it's a solid substance at a room temperature conditions. It has an inorganic origin, and then we can define that particular material using a chemical formula, and also it has a crystallinity or crystalline structure. So majority of gemstones are minerals, but in addition to that, so some of the rocks, so rocks mean it's an aggregate of one or more minerals. And sometimes we can identify non-mineral materials like fossils or some natural glasses, especially in volcanic rocks. So there are some rocks, actually, we can consider them as gemstone. And some amorphous material. In mineralogy, we call them as mineraloids. So mineraloids mean actually those materials haven't crystallinity or crystalline structure. They are also naturally occurring homogeneous solid. We can define them using a chemical formula, but they are lack of crystalline structure. In addition to that, some of the organic substance, some of the substance or material, they are secreted by some organisms. They are also considered as gemstone. There are some materials. So this substance, so they have been valued for their beauty because they are very beautiful materials, and durability is very high in the nature. They are very rare. So those are the characteristic features related to gemstones. So then people find or extract these rare, beautiful, more durable materials, and then they cut and polish those materials to produce jewelries and other ornaments. So when we are considering the history actually, so the history of gemstone that extend several centuries. So in some cultures, it's a significant substance. For an example, people use for healing practices, like some of the gemstones are used for or doing some of the therapies. And also it's a type of symbols to show the status of some people. For an example, in Asian kings, so they prefer to collect different gemstones and store in their treasury. So that's a iconic material to show their richness. So usually this gemstone actually in tradition, so gems we can classify as precious gemstones and semi-precious. Precious mean actually there are 4 minerals mainly. So ruby, sapphire, diamond, and emerald. So these 4 mainly in history actually people consider them as very precious gemstone after considering their rarity and beauty mainly. So these things I already explained some of the mineraloids or amorphous materials. For an example, opal, precipitated hydrated silica. It is considered as a semi-precious gemstone. And some of the rocks, for an example, this is one of the example, lapis lazuli. It's a type of rock. It's contained more than 1 mineral. It's an aggregate of minerals, especially the mineral called lazurite that give this beautiful color, blue color. So as a result, people use it as a gem. And some biogenic material like pearl. So it's in its composition, it is calcium carbonate, but they produce by organisms. So they are also due to their rarity and beauty, people use those materials as gems. The next question is, why are gemstones rare? So I think when we are considering minerals, so sometimes in the nature, we can identify some of the very common minerals. If you take a soil sample or sometimes you can identify some fragment of quartz, some feldspar, some fragment of mica, like very common minerals. But gemstones, they are very rare in the nature. It means they are not commonly available. So what are the reasons for that? So in this section, we will briefly discuss the possible reasons. So what kind of reasons affect for this, the rarity of gemstones? Why are gemstones rare? So under that, actually different factors may affect. So here I'm going to discuss about 5 or 6 factors. So these are some of the reasons. So due to that, gemstones are rare in the nature. So mainly that control the geological conditions that necessary for formation of gem quality materials. So as a result, gem deposits are rare in the nature because the required conditions or geological conditions necessary for formation of gem quality materials are rarely attained. So what are these geological conditions? So first, so here, so I have listed 2 things. So if you consider a gem, you can identify, so they are made from atoms, or which means elements. So if you consider a mineral, you can define it using a chemical formula. Quartz means silicon dioxide. It means available elements are silica and oxygen. Corundum, aluminium, oxide. So essential constituent are aluminium and oxygen. So likewise. So when we are considering the planet Earth, it's a differentiated body. It means its composition is not homogeneous from crust to core. So as a result, the element distribution that is not homogeneous. In some of the environment, some of the elements, they are rich in the crust. Some other elements, they are commonly available in earth mantle. Sometimes some other elements within earth core. So it means the availability of major constituent. Some of the occasions, they are not very common in the nature. We will take some examples. In addition to that, so gemstone frequently you can identify a very beautiful color. So to formation of this beautiful color, so color of a mineral actually that can effect that can produce through various reasons, but most of the occasion, the presence of sufficient amount of chromophores. Chromophores mean actually these are some ions. So these ions can absorb particular wavelength from the visible light spectrum. So then the remaining wavelength can combine and produce a color. So especially when you're considering chromophores, that is the main coloring agent of gemstone. That is not the only coloring agent. It's mean chromophores mean those are type of ions. So especially when you are considering the periodic table, most of the chromophores that are available in gemstones, they are D block elements, transitional metals actually, these are. So due to their unique or specific electron configuration, so it's contained some unfilled position in D, this particular shell. So as a result, so these particular transitional metals, so these D block elements can absorb, so these electrons can absorb different wavelengths from the visible light spectrum. So then they can jump into different levels. So as a result, we can identify, so incorporation of these chromophores that result a beautiful color. For an example here, ruby. So that is the main constituent here, the main constituent of ruby, that is aluminium oxide. So in this case, but if that particular mineral that contains only aluminium and oxygen, so you cannot identify beautiful color. Sometimes it is colorless. But under the presence of chromium as an impurity, so chromium can substitute into the corundum structure, replacing aluminium, because aluminium also has +3 charge, chromium also has +3 charge. They are ionic radius slightly similar approximately. So as a result, chromium can incorporate into this corundum structure. So chromium, due to its specific electron configuration, that can absorb some of the wavelength. So here, these are the absorption color spectrum. So this is the normal visible light spectrum. So that extends from 400 to 700 nanometer in electromagnetic radiation. So here you can identify mainly wavelengths around 550. And here they are absorbed by this grain. So more red color can transmit or reflect. After combination of these colors, the remaining wavelength, so you can identify this beautiful color related to ruby. So here, this is another example. So this one, this is emerald. Emerald means actually it's a beryl group. It's a type of beryl. So here, so this is the normal chemical formula. Essential constituent, beryllium, aluminium, silica, oxygen. So without this element, you cannot define this mineral. So these are the essential chemical constituent. But so during formation of emerald, actually, so emerald and beryl, so these different terms. So in gemologists mainly, so people, they are expert on the field of actually for identification, classification, cut and polish of gemstone, we call them as gemologists. So they use sometimes different terms. So we mean actually mineralogists or petrologists, they use the mineral name, but gemologists use separate terms. So emerald is such a name. Ruby also like that, but the mineral is corundum, contain chromium as impurities. In this situation also, chromium can substitute into this mineral structure. So in this case, the availability of, so here also actually aluminium remove, chromium can incorporate. But when we are considering the surrounding environment, the bond strength, so here the surrounding elements are aluminium and oxygen. Here the surrounding elements, they are beryllium, aluminium, silica, oxygen. So effect of these different elements on chromium in corundum structure and emerald structure, they are different. So as a result, here, this mineral can absorb different wavelength the chromium can absorb different wavelength compared to ruby. So in both minerals contain chromium as impurities. So due to the effect of the surrounding elements, due to variation of bond strength, actually chromium here, they can absorb mainly wavelengths from around 600. So most of the red colors in this region, so you can identify dark regions, which means these wavelengths are absorbed here also. So after combination of remaining wavelength, that result this very beautiful green color. So that's the some basic information related to chromopores. So considering gemstone, actually there are some major constituents. So some of the chromopores, they could be a major constituent. So in this case, they are impurities. But if you consider this particular mineral, so it's also a semi-precious gemstone, rhodocosite, manganese carbonate. So here manganese, it's a D block elements. It can absorb some of the wavelength, but this is not an impurity. Manganese here, it's not an impurity. It's a major constituent. So chromopores or the coloring agent of rhodocosite here, that is one of the major element of its chemistry. But emerald, ruby, impurities, they are the chromophores, coloring nature. So if you further consider, so these two, so don't confuse actually, not only chromophores, it means not only elements. Sometimes color could result due to various reasons, sometimes during refraction, sometimes under the availability of defects in the crystal structure or color centers. So there are different reasons that could control the color of a material, but most of the occasion we can identify in gemstone, most of the occasion we can identify the availability of chromophores. So these major elements and chromophores or the coloring nature, they represent ingredients for gem formation. So ingredients mean those are the essential component to formation of those different gem varieties. So it is like that. If you consider, if you are plumbing to it vanilla tasted butter cake like that, so these are the ingredients. So without these ingredients, the essential materials, you cannot produce this ultimate product. So these are the some of the examples. So likewise, when you are considering gemstone, actually we can define a chemistry or chemical formula related to that. For an example, diamond means carbon. Ruby, that is essentially aluminium, oxygen, likewise. So ingredients, so essential elements play a key role. So but the problem is sometimes some of the element distribution, since the earth is a differentiated body, this element distribution is not homogeneous. In some environments, some of the elements are very rare. Like this one, it is not commonly available element in most of the environment, geological environment. So here, if you consider, you can get an idea about further after considering diamond. So diamond, the formation of diamond, essential requirement is the availability of carbon. And the second one, the high pressure conditions and high temperature. So those are the essential components, essential requirement. But usually the required pressure conditions that is available under the earth mantle condition, probably upper part of the mantle. So that the available pressure here that is suitable to formation of diamond. But when you are considering the available chemical constituent, carbon is a trace element in earth mantle. It is not commonly available. It's a very rare trace element. For formation of gem quality diamonds, one of the requirement is local enrichment. Through the different geological processes, carbon should enrich in some part. So then high pressure and temperature conditions are available. Enrichment of carbon also had happened. So that is a suitable environment for formation of diamond. So that's why diamond is very expensive. It's very rare. So if you consider this particular example, further understand about the role of ingredients. So emerald. So it is a type of chromium or vanadium bearing gem beryl. So these are the essential constituent of beryl, but coloring agent is chromium or vanadium. So these are available as impurities. When we are considering the geological environment related to distribution of these different elements, so usually emerald, this particular gemstone, we can identify within the earth crust, like associate with pegmatite. Today we will discuss pegmatite. So pegmatite, they produce within the middle part of the earth crust. But when you are considering the element distribution, so here beryllium, it is a trace element in the earth crust. So this is the average abundance contained. So that is not sufficient to crystallize this particular mineral. But some of the geological processes, such as fractional crystallization of magma, that allows to enhance the concentration or increase the concentration of beryllium. So then usually aluminium and silica is commonly available element in the earth crust. So after enrichment of beryllium, that is possible to crystallize beryl. But to produce emerald, the requirement is chromium or vanadium, that is the chromophores or the color in nature. When you are considering the distribution of these two elements, usually chromium, that is mainly available in mafic rocks or ultramafic rocks. So they are mainly available within Earth upper mantle, especially dunite, peridotite. When you are considering this one, vanadium, that is available usually organic rich environment, because organic materials can absorb vanadium from solution. This is mostly stable under reducing conditions. So as a result, ion precipitation conditions, reducing conditions, mostly suitable for stability of this one. So they survive in different environment. So to formation of emerald, what is the requirement? Chromium or vanadium, beryllium, aluminium, silica, oxygen should meet together. It's a very rare situation. So geological process, so during fractional crystallization, beryllium can enrich. So sometimes during pegmatite, that is specific rock, that igneous rock, if the particular pegmatite contain beryllium, and if it intrude into a mafic or ultramafic rock, like that. So this is one of illustration. So then at the rock contacts, at the surface in between these two rocks, chromium, because mafic and ultramafic rocks contain chromium. This chromium can reach us towards this pegmatite. So at the surface, at the contact, this beryllium bearing pegmatite and this mafic or ultramafic rock, there is a possibility crystallization of emerald. So that is one of the classic model, most commonly used model for emerald formation. So then you can get an idea how it's difficult for these different elements survive or stable in different environment. So that is the role of ingredients for gem formation. In addition to that, we can identify some of the elements, we consider them as undesirable elements. It's mean they negatively affect on formation of gems. One example, when we are considering the earth crust, so these are the element distribution. Oxygen, that is the most dominant, then silica, and then aluminium. But quartz you can frequently identify in the nature, but corundum, aluminium is third dominant element, but you cannot identify corundum everywhere. What is the reason? The reason is under the presence of silica. So silica, that is act as a kind of undesirable element that prevent corundum crystallization or formation. Under the presence of silica, so aluminium and oxygen combine with this silica and produce silicate minerals like feldspar, muscovite or aluminosilicate like sillimanite, kyanite, because for formation of corundum, the requirement is silica deficient environment. Then only aluminium oxide can produce. Although aluminium is dominant in the crust, corundum is a rare mineral. That's the reason, because under the presence of silica, that prevent formation of corundum. Instead, some other silicate minerals, aluminium and silica bearing silicate, like feldspar, mica, are produced. In addition to that, actually, some of the elements, even some of the chromophores, under the availability of high concentration, they can negatively affect on color. Sometimes, so here, some of the example. So more chromium, sometimes it's a poison for gems that over dark green color produced on emerald. Sometimes availability of high concentration of iron. So this type of black tourmaline. So its economical value is very low. But here, if under the proper concentration of chromium, manganese-like elements, so very nice crystals can produce. So in the particular environment, during gem formation, the limited concentration of undesirable element also play a key role. If those elements are present, that affect negatively during gem formation. So that is another factor. So sometimes open space. So this is actually, you can identify this as a geoid, open cavity. Within that, amethyst has been crystallized. So here, like that. So under the presence of free space, some of the minerals can produce very nice crystals. I mean, very nice crystal faces. So, but that is not a common situation in most of the environment, especially middle to deep part of the crust. In upper part of the crust, especially in sedimentary rocks, it's possible. Sometimes in volcanic rocks, during separation of dissolved air, some large air bubbles can naturally produce, and later this air can release from this rock mass, produce in empty space, and after that dissolved silica sometimes can reach to this empty space, and silica can crystallize. It means quartz can crystallize, because if iron is available in that environment, so iron can incorporate into that quartz structure. So then that's how amethyst produce this particular. So this is a very common example. But for some of the gems, actually, it is not essential for the availability of free space like this. Even in high-grade metamorphic rocks, they contain interlocking textures. You cannot identify free spaces among mineral grains, but gem quality minerals can produce. But some minerals, under the presence of free space, they produce very nice crystals, euhedral crystals, like that. So these are not cut and polished one. This is the natural shape. The next thing is the optimum pressure temperature conditions for formation, because different minerals, they stable under different pressure temperature conditions. So I will go back into my previous example. So here, these are the ingredients to produce a butter cake, vanilla flavored butter cake. So if you mix them according to the relevant proportion, according to the recipe, 500 grams of flour and then 5 eggs, like that, according to the recipe, you mix it. The composition is suitable to produce a butter cake, but this mixture you cannot consider as a cake, because you need to provide the optimum temperature condition. Sometimes you have to keep this mixture 30 minutes under 150 centigrade, like that. So minerals also like that, because different minerals stable under different pressure temperature conditions. Sometimes the particular rock may contain all the required ingredients or essential elements for formation of different gem varieties. But these rocks should reach us to optimum pressure temperature conditions, then only those minerals can produce, especially during. So this is very common example. We will rediscuss this under metamorphic rocks very briefly. So here, kyanites. Some of the kyanite, under the presence of impurities like iron, that can yield this beautiful blue color. But the requirement is relatively high pressure and relatively low temperature. But sillimanite, it's mainly stable and high temperature condition. So the summary is majority of gemstones or gems are minerals. Minerals, they represent different stability field. Different minerals represent different pressure, temperature, stability field. So these are some other conditions. So just assume that after mixing of the relevant ingredients, the particular rock reaches to the optimum pressure temperature condition to formation of one of mineral, one of gem mineral. But after its formation, this particular mineral should preserve from post-growth damage. Post-growth damage means, for example, this is garnet, a beautiful cut and polished garnet. In most of the rocks, you can identify garnet, but you cannot use them as gemstone because they contain large amount of fractures and large amount of inclusion sometimes. So in a gem, clarity is one of the important factors. It should be inclusion free. There are some gem varieties, inclusion at additional value for them, but majority of gems, the presence of impurities like inclusions that may negatively affect for its value, and also the availability of fractures. So under the presence of high amount of fractures, you cannot cut and polish it. So usually garnet like minerals, they produce during metamorphism, they produce middle to deep part of the crust. So then just assume, so minerals they produce here, but you have to extract them from the earth's surface. It means these rocks should reach us to the or uplift to the earth's surface due to erosion and isostatic equilibrium sometimes. So different geological processes contribute for this upliftment. So then what can happen? So here pressure is relatively high. Now overlying rock masses removed away. So as a result, at the Earth's surface, the pressure is lower towards the Earth's surface. So then these rocks and some of the minerals, they experience volume expansion. So here they store or available under high pressure conditions in this part. So some of the garnet can produce here. But during upliftment, due to removal of this overlying weight, what can happen? Garnet can experience volume expansion. Then fractures can develop. So mechanical fracturing, that's a negative effect for the value of gemstone. And chemical weathering, because after reaching to the Earth's surface, some of the materials, minerals are highly unstable. They heavily experience effect or attack by chemical weathering. Best example is olivine. So gem quality olivine, in gemologists, they call it as peridot. So this is the formula is olivine. So this particular D blocks element, Fe2 plus can result that can absorb some of wavelength. The remaining wavelength of the visible light spectrum can create this particular color. But olivine, it's very difficult to survive at the Earth's surface because in that case, what can happen? Olivine can transform. So here, under the presence of different fluid, olivine can interact. Olivine can convert into serpentine group minerals. Sometimes at the Earth's surface, that experience hydrolysis that interact with water and dissolve under slightly acidic or under different condition in weathering environment. So as a result, so after formation of that, they should actually preserve from mechanical fracturing, chemical weathering, sometimes metamorphic reactions, especially in metamorphic rocks. If gem form in the metamorphic rocks, because in metamorphic rocks, with respect to variation of pressure temperature conditions, minerals are reactive, producing new minerals. Those new minerals are stable under the new environment, under new pressure temperature condition. So sometimes under high pressure conditions, a gem quality garnet can produce. But then during cooling, during upliftment, this garnet can break down. So you may, if you prepare a thin section, sometimes you can identify relics for the availability of garnet in that rock. So likewise, after formation of a gem quality mineral, those gem quality minerals or materials should preserve from post-growth damage. So these are some of the factors. So due to these reasons, now you can get some kind of idea why gemstones are rare, why they are not commonly available. So I discuss only few facts. So here we discuss these things, and now I hope you should have some kind of basic idea behind why are gemstone rare. So after that, so we will discuss some of the examples related to geological origin of these gems. So first, I have listed some of the mechanisms that contribute to formation of gem quality materials. So igneous process or igneous origin. So igneous rocks mean those are product after crystallization of magma and lava. So during crystallization of magma or lava, gem minerals can produce. For an example, some of the volcanic glasses, they also act as some amorphous gem material. And sometimes some of the igneous rocks, actually they play a role. For an example, we will discuss that is also in the next section. So they act as transporting, actually for transportation. Some, for an example, diamond, they produce within the earth upper mantle. So there are some igneous rocks, they contribute to transport those produced diamond from the earth mantle to the earth's surface, like kimberlite. So during metamorphism, especially metamorphism, so during metamorphism, what is happening, the textures and mineralogy of pre-existing rock or the parent rock experience changes. New minerals will produce, new textures will produce. So these are happen mainly through the metamorphic reactions. So during this metamorphic reaction, gem quality minerals can produce. And sedimentary environment, sometimes some minerals can precipitate in some sedimentary environment. So sometimes a hydrothermal origin mean actually within the earth interior, especially in the earth crust, there are some water-rich, high-temperature fluids. So they contain high amount of dissolved ions and molecules. So this, during cooling of this hydrothermal fluid, or sometimes this hydrothermal fluid or ion and molecule dissolved hot fluids can interact with the surrounding rocks. So then that facilitate to produce very beautiful minerals. Sometimes metasomatic process, as I mentioned earlier, the contact between pegmatite and ultramafic or mafic rock. So some of the materials exchange, some of the materials, so as indicated here, so some of the materials, because emerald produce in most of the classical model at the contact between these two rocks. So some of the elements should reach towards from this mafic or ultramafic rocks. So some of other elements should move from this pegmatite towards this contact. So that is we called as metasomatic process. It's an open system behavior. So usually metamorphism, except for volatile materials or gases, so it is usually, it's happened in closed system, because except for volatiles, other elements in parent rock and the produce metamorphic rocks, they are approximately similar, their concentrations. So it's a relatively closed system behavior. But metasomatism means an open system behavior. So as I mentioned very earlier, sometimes some materials represent biogenic origin, like amber. So it's a kind of product after sedimentation, but the original material could be some resins secreted or produced by some plants. So sometimes pearl. So like that. But here, due to the availability of time, I take some examples for origin of gems in igneous rocks and some metamorphic rocks. So first we will discuss the situation related to igneous origin. So how gems can produce within an igneous system. So sometimes, so here I have listed, so sometimes directly gem quality stones or minerals can crystallize from magma during crystallization of magma within the earth interior. So occasionally, so during crystallization of lava sometimes, under the presence of high dissolved gas content, because if you consider magma, so majority of it's a molten rock, but when you are considering the available materials in magma that mainly contain so ions and molecules, in addition to that, some dissolved gases like water, carbon dioxide, and some volatiles, we call them as volatile materials. And then sometimes that contain already crystallized minerals. It's a combination of that. So some of the magma contain up to 1 to 9% of dissolved gases. So because these dissolved gases mean these gases can available under within the earth interior, pressure is relatively high. So that facilitate to those volatile materials exist as dissolved gas phases in with magma. But when they reaches to the earth, those materials reach to the earth's surface, pressure is drastically dropped. So then these dissolved gas phases try to escape from magma. At the earth's surface, we call it as lava. So then what can happen? So during that process, sometimes relatively large gas bubble can produce within flowing lava. So after some time, these gas phases can escape due to fracturing of the rock. These gas phases can escape from the body, but that create empty space within the lava flow. So later, sometimes groundwater that can transmit through these fractures, they can reach us to that empty space or the available cavity. And that provide favorable condition for crystallization or precipitation of actually some of the minerals within the cavity, within that open space. So that's how some of the geoids produce in volcanic terrain. Amethyst bearing geoid. So the summary is up to now, sometimes some of the gem quality minerals can directly crystallize from magma. So sometimes crystallization of magma or lava, especially gas, volatile dissolved lava, that can create suitable space or cavities to produce secondary or precipitate secondary minerals. And sometimes some of the igneous rocks, they act as actually transport in nature. So the best example is kimberlite. So kimberlite, actually they act as transporting agent. So mainly a diamond, the produced diamond within the earth mantle, they reach to the earth's surface through this kimberlite magmatism. So first, we will take one of the very common example when you are learning about or engaging with the formation of gems in igneous rocks. So pegmatite, this particular rock type, that play one of critical role, because pegmatite means actually it's any type of igneous rocks contain very coarse interlocking crystals. But in the nature, commonly you can identify granitic pegmatite. So large crystals, sometimes one crystal, its size or average diameter, sometimes several centimeters. So some of the crystals, sometimes its length more than 1 meter, large coarse grained crystal. And granitic pegmatite means the composition or the mineralogy, because mineralogy represent the composition of a rock, because minerals are chemicals. the available minerals are very similar to a granite. So usually granite contain minerals like alkali feldspar, quartz, and some minor amount of some mafic minerals like hornblende or biotite. The composition wise or mineralogically, so this some of the pegmatite or majority of pegmatite, they represent, they are chemically equivalent to a granite. So then we call it as granitic pegmatite. So sometimes some of the granitic pegmatites, they act a suitable source to formation of different gem varieties, not all the pegmatite. So in the nature, most of the occasion, 1 or 2% of granitic pegmatites, they act as source for different gemstones. Because this pegmatite means it's 100%, this is a small scale one. So the sum of the pegmatite, yeah, average size more than 1 or 2 or more than that, the square kilometer size, large scale pegmatite bodies. So especially in historically countries like Brazil, Madagascar, Russia, or United States, so these countries contain this particular gem-bearing large-scale pegmatite. But recently, some Asian countries, or Afghanistan, even some Sri Lanka, so India, likewise, is reported gem quality minerals bearing granitic pegmatites. So when you're considering these granitic pegmatites, actually they can act as, so in various ways. For an example, it is 100% mineable rock. For an example, large, so here you can identify large grains of quartz and feldspar. So these large quartz and feldspar, actually we can mine for different industries. So we call them as industrial minerals like quartz, feldspar, mica. We use them in different industries like porcelain industry, tile industry, ceramic industry, likewise. So sometimes these pegmatite contain minerals. Those minerals contain strategic metals. Strategic metals mean those metals used in high technology related industries. So there are some minerals in this granitic pegmatite. They contain those rare, sometimes rare earth element bearing. When you are considering, I hope you are familiar with rare earth elements. So some of the minerals, they are rich with this rare earth element, are contained or are available with this pegmatite. So sometimes there are some pegmatite that contain energy minerals. Energy minerals mean especially thorium or sometimes uranium rich minerals, because we can extract thorium or uranium for power production in nuclear power plant. So likewise, there is a possibility some of the pegmatite contain gem quality gem minerals. So what is the reason for that? Why this rock is very specific, that contain some unusual mineralogy? In addition to quartz, feldspar, mica, some of the pegmatite, if a pegmatite, granitic pegmatite contain quartz, feldspar, and mica, usually we call it as barren pegmatite. It has only industrial use. You can mine it only to extract quartz, feldspar, like industrial mineral. But sometimes the situation is different. So what is the reason for that? Why this some rare, unusual minerals or mineralogy that is available with this pegmatite, including gems? So that is, there are different mechanisms are used to different hypotheses. Sometimes in the history, people invented to explain the formation of these granitic pegmatites out of them. So widely used, most acceptable method, this is one of the mostly acceptable method, fractional crystallization of granitic magma. So what is fractional crystallization? So fractional crystallization provide suitable condition to enrich some of the elements. For an example, I mentioned emerald. So usually beryllium, that's a very trace amount of beryllium is available in earth crust, but fractional crystallization provide a suitable platform to enrichment of beryllium. So what is fractional crystallization? It is like this. If you consider this, we can get an idea after using this example. Just this is a vegetable soup. So you can identify some of the pepper and chili particles at the top. They are floating. So if you taste the initial part of this soup, the liquid fraction, sometimes you may experience more spicy. If you consume considerable volume of this liquid fraction, what will happen? The spicy content, there is a possibility because you consume all the floating red chili and this pepper, then the nature of the spicy nature, that feeling gradually decrease. So likewise, then you will eat this vegetable fragment. And if you consider the final fraction that is available at the bottom, at the late stage, you will experience different taste. The summary is, with respect to the time, if you carefully pay attention, you can experience different taste, different nature of spicy. So during magma cooling, we can identify the situation like this. This is the parent magma, original magma body. So during magma cooling, what can happen based on the melting points? So different minerals crystallize. That is, there is a linkage between the composition of this parent magma and the crystalline phases. If iron and magnesium is available, iron and magnesium bearing minerals can crystallize. If magnesium is not available in this parent magma, magnesium bearing minerals cannot crystallize here, because the chemistry of these crystals that controlled by the original chemistry of this parent magma. When you are considering, so magma contain mainly molten rock materials, mainly iron and molecules, plus some of the already available solid particles, and sometimes some magma may contain dissolved gases or fluid phases. So when you are considering elements in the periodic table, some of the elements, during cooling, they always prefer to accommodate within crystal structure. We call them as compatible element, like iron, magnesium. So during cooling, they mainly incorporate into these crystalline materials. If this is iron and magnesium rich magma, there is a possibility olivine can crystallize. So olivine mainly contains silica, oxygen, and mainly iron and magnesium. There are some elements, they always prefer to stay within the fluid phase, within this liquid portion. They don't prefer to incorporate into this solid. Such elements, we call them as incompatible elements. So incompatible, they are not prefer to incorporate into the solid particles. So during cooling of magma, what is happening? Compatible elements, they mainly store into these crystallized minerals. The concentration of the incompatible elements, they gradually increase. So here, just assume there is an incompatible elements, mean they are mainly elements having large ionic radius, or sometimes large high charge. We call them as high field strength element, like zirconium, niobium, hafnium. Large ionic radius, especially group 1 elements like lithophile elements, like we can consider potassium, rubidium, strontium, likewise. So they always stay within the remaining liquid or residual magma. So here, the concentration of available zirconium or hafnium, incompatible concentration in this one, and here they are different, because incompatible element concentration gradually increase. So dissolved gas phases. So initially, during magma crystallization, they mainly produce anhydrous mineral. So as a result, the availability of the dissolved water and other gas phases, their concentration also gradually increase from here to there. So that is we called as fractional crystallization. During fractional crystallization, what can happen? Some of the elements, their concentration can drastically increase. Enrichment sometimes happen 100 times, 1,000 times. Some elements up to 10,000, no more than that. So that's the nature of fractional crystallization. So pegmatite, they produce at the last part of this fractional crystallization of granitic magma. So here, from this magma. So here, incompatible element concentrations. So incompatible elements are mainly rare earth elements. So like high field strength element, like zirconium, niobium, hafnium, rare earth, thorium, uranium, tantalum, likewise, or large ions having large ionic radius. So then their concentration drastically increase here. So then what can happen? If this magma experience further cooling, the volatile component. So here volatile components like dissolved gases, like chlorine, fluorine, this substance, their concentration is drastically high. So after some point, they cannot further exist as, remain as dissolved material. Because in any material, you must know there is a limit called solubility limit. So if you consider there is a, under the given temperature and pressure condition, if you are going to dissolve some substance or solute, and then there is a maximum limit. Beyond that, you cannot dissolve that material within that solvent. So likewise here, because these volatile phases, sometimes their concentration drastically increase and then they start to separate. We call it as immiscible state. So then these volatile rich pockets can produce within this late stage of this magma. So surrounding one, they are the normal iron and molecules bearing magma. So within that, these are exfol volatile rich pockets. So here, not only water or carbon dioxide, some dissolved ions are also elements, different elements can be available. So if the situation is further continue, the cooling is further continue, what can happen? So here, very rare, because here incompatible element concentration is very high. So then incompatible element rich mineral phases can crystallize in pegmatite. So under that, some of gemstone, some rare gemstone can also produce. Not only gemstone, some other energy minerals or sometimes some strategic metals bearing minerals can crystallize. So as a summary, these considering pegmatite, so pegmatite contain more than 50 familiar gemstones. So they occur mainly as silicate, sometimes oxide, phosphate, likewise. But when you are considering the available gemstone in pegmatite, their size is relatively smaller compared to other industrial minerals. Sometimes you can identify very large mica crystal, biotite mica, very large feldspar crystal. Those are industrial minerals. But considering the size of gemstones, they are relatively smaller compared to other common industrial minerals like quartz and feldspar. But there are some examples in some countries like Brazil, some of the very large gem quality aquamarine crystal. It means it's a type of berry group mineral. So here, impurities are mainly iron. So emerald, it is the impurity, mainly chromium or vanadium. So there are some very huge, large crystals have been reported. So here, this is one of the examples. So this part, I already explained the origin of gem forming melt, as I explained here. So have summarized here also. Actually, I will give this presentation to Dr. Athira. So probably she will circulate it with you. So exsolution of or separation of volatile rich pockets, how it is happening. So this particular term I will later introduce. So So when you're considering the anatomy of large pegmatites, so usually, so I mentioned previously some of the pegmatites, their size, average size would be several square kilometer. So then the mineral distribution of those pegmatite may not homogeneous. We call them as pegmatites are zone, mineral zonation we can identify from rim to core. So the reason is, so most of this occasion, so pegmatite, so they intrude as dikes or seals. So this is the country rock according to this example. So this is a small is actually outcrop scale one. So this is the country rocks. So this is the intruded pegmatitic melt and crystallize to produce a pegmatite. So during this intrusion, so that is during the middle part of the earth crust, most of the occasion, the temperature of country rock is relatively lower compared to the pegmatitic melt. Sometimes just assume here temperature during intrusion age. Not so this is the exposure at the surface, but during formation, sometimes here temperature would be 600 or 700. Country rock, sometimes according to the geothermal gradient, the temperature would be 500. So as a result, so here at this contact, so usually crystallization, majority of occasion, most of the occasion, crystallization that initiate from this rim. Mineral crystallization here initiate first, and then gradually that continue towards the core. The minerals at the core region in most of the core zone pegmatite that happen at the last part. So now it is linked with fractional crystallization. So as a result, mainly incompatible element rich mineral phases. There is a possibility you can identify they have mineralized at the core area. So when you are considering pegmatite, actually we can identify the origin or formation of gems in three main zones. Because don't confuse all the pegmatites, they don't contain gemstone. In the nature, about 1 to 2% of granitic pegmatite contain gems because gems are rare. So I mentioned some reasons why are gemstone rare in previously. So here, when you are considering the pegmatite anatomy, some of the pegmatite, they mainly concentrate at the core region, the central part, that is the late stage of the crystallization happen here. So then some unusual, uncommon minerals can produce in this part. The second zone is the actually contact between the pegmatite and its surrounding rock. As I mentioned earlier, so here, so this is pegmatite, the country rock, the surrounding rock. At the contact, due to metasomatism, due to exchanging of some element, some of the materials, they move from pegmatite towards this contact. Some other materials or elements, they come from this ultramafic or mafic rocks or the country rock towards the contact. At the contact, some unusual minerals, very rare minerals can occur due to mixing of those different chemical compounds. So that is the second setting at the contact with this pegmatite and the surrounding country rock. The third setting is, we call it as myrolitic cavities. Myrolitic cavities, they mainly form during this particular process because pegmatic magma contain considerable amount of dissolved or volatile materials, but during continuation of the fractional crystallization, these volatiles cannot exist as dissolved materials. They start to separate or exhale. So then these exhale fluid-rich compounds, so here, because they contain not only volatiles like gases, water, chlorine, that contain some dissolved iron and molecules. So they can crystallize, producing minerals within these spaces. We call them as, in pegmatite, we call them as myrolitic cavities. So here, one of the sketch showing. So within this cavity, we can identify crystallization of different minerals. Some of them are gem quality. So this is one of the example. So here quartz feldspar. In addition to that, gem quality tourmaline can produce based on the available chemistry of those melt water pockets. But this also a rare situation. So myrolitic cavities bearing pegmatites are very, it's not common actually. Gem pockets bearing pegmatite. So that is the things related to pegmatite, how that particular rock contribute to formation of some gem varieties, how these different rare gem varieties, what is the available conditions for formation of those rare gem varieties associated with pegmatite. So next we will briefly discuss about the role of kimberlite. That is also a type of igneous rock. So kimberlite means it's a mantle derived ultra basic rock, but they mainly erupt at their surface or sometimes crystallize as hyperbasal rocks, very shallow depth. Volcanic mean at their surface. So they contain considerable amount of dissolved gases or fluid, carbon dioxide, water. So that's the reason. Usually ultra basic magma, I hope you may heard that cometite, because their density is very high. So as a result, it's very difficult to reach this high dense magma to the Earth's surface. But kimberlite, due to availability of these volatiles, that effect of its density, so kimberlite can reach us up to the Earth's surface level. So here, this particular diagram represents the reported kimberlite. So mainly you can identify some clusters, well distribution of kimberlite in South Africa, western part of Australia, and here in American side or Canadian side. So that is the main delivery system of Earth diamond. So usually Earth diamond, majority of diamond produced within this lithospheric mantle. So when I hope you are familiar with what is lithosphere. Lithosphere means, so when you are considering the Earth crust plus the uppermost mantle, we call it as lithosphere. So that's how we can define lithospheric plate. They are moving here and there. So lithospheric mantle means the particular mantle section of the lithosphere. So here mainly the temperature and pressure conditions especially suitable to formation of diamond under the presence of carbon. Everywhere diamond cannot produce, but under the presence of carbon and some other factors, not only carbon, some reducing factors, there are different factors effect for the diamond crystallization. If the particular area of the mantle that can fulfill those factors, diamond can crystallize. But this diamond can reach us to the Earth's surface through this particular igneous rock, kimberlite. So like that. So this is the kimberlite, that rock. So this is one of example. Diamond crystal, we call them, this is a foreign mineral, xenocryst in igneous petrology. So this diamond didn't produce within the kimberlite. Kimberlite contributed to transport that from Earth mantle to the surface. So those are the things actually with the available time I would like to discuss about under the igneous origin. So then very briefly, about next 5 to 10 minutes, I will spend to discuss about metamorphic origin. It means some of the gem quality minerals that produce during metamorphism. So metamorphism, as I explained earlier, during this process, metamorphism actually, the mineralogy and mineral textures of its parent rock experience various changes. New minerals can produce, new textures can produce. So here we can define, after studying of the available minerals and textures in a metamorphic rock or a series of rock in a terrain, after studying of different type of metamorphic rock in a terrain, we can define this pressure temperature path, PT path, we call it as. So here what is happening, actually, the experience pressure and temperature conditions during its evolution. So here this graph is a very fundamental one that describe, that represent the stability of different common rock forming minerals. So especially these minerals you can identify in pellitic rocks, aluminium bearing rock. So here, so with respect to variation of these pressure and temperature conditions, the mineralogy of the metamorphic rock also vary. So as a result, we can identify, actually, when you are considering this particular cycle, we call it as PT path. So this is the maximum temperature conditions experienced by the particular rock. So in metamorphic petrology, we call it as peak metamorphic condition. All the pressure temperature conditions prior to peak metamorphic conditions we called as prograde metamorphic condition. And all the pressure temperature conditions experienced by this rock after the peak metamorphism or maximum temperature conditions, we call them as retrograde metamorphism. So all these stages, mineral reactions are taking place. So here, the available mineralogy, they can survive under relatively high pressure. From here to there, pressure decreasing, so some of the minerals become unstable. So they can break down, producing new minerals. So there is a possibility gem quality minerals can produce sometimes here, but during metamorphic reaction, those gem quality minerals can break down. So this is one of the example, aluminosilicate, those under the presence of suitable, that particular color, clarity, inclusion-free nature, fracture-free nature. Actually, we can consider some of the kyanite as gem quality kyanite, some of the sillimanite as gem quality sillimanite, some of the andalusite as gem quality andalusite. They are not common. Sometimes in high pressure terrain, kyanite is a common mineral. In high temperature terrain, sillimanite is a common mineral in some of the rock type, but they are not in gem quality. Sometimes due to impurities, sometimes due to the availability of cleavages, fractures, sometimes grain sizes are very small. So that's the reason. So always you cannot expect gem quality sillimanite in a high grade metamorphic terrain. If a terrain experience high temperature metamorphism, sillimanite can produce. Sillimanite is available in different rocks if the chemistry is suitable, but they are not in gem quality. So they stable under different pressure temperature condition. That is another, because sometimes gem quality, this type of kyanite can produce here. Then during variation of pressure and temperature, this kyanite can transform into sillimanite. Sometimes these are small sillimanite grain. Initially, there was a gem quality large kyanite crystal, but this kyanite can experience phase change. Here also mineral chemistry similar. Here also mineral chemistry, they are polymorphs. Sometimes the sillimanite, they are relatively smaller grain. They are not gem quality. So considering gem deposit associated with metamorphic terrains, so in addition to, there is a possibility you can identify this type of aluminosilicate even in my country, Sri Lanka. So gem quality sillimanite that is available. Some in gem deposit, they are mainly secondary deposit. Secondary deposit means primary deposit is the original rock, this mineral bearing rock. But after weathering these particular minerals, so these are cut and polished grains, these minerals can erode away and deposit, producing sometimes a alluvial deposit. So people mine those alluvial deposit to extract those gem quality minerals. The parent rock, the original rock, sometimes a metamorphic rock, sometimes a pegmatite. So this is one of the, this is actually rock, jade. So that is used as a semi-precious gem substance. So it's not a single mineral. So it has a very nice So beautiful green color. We call it as emerald green. So here we can identify, actually it's a combination of several minerals. So jade mean frequently people use it as a rock contain mineral jadeite. So sometimes some of the jade, this green color due to this nephrite itself. So here this is a pyroxene, this is an amphibole group mineral. So here I'm going to discuss mainly about jadeite bearing jade. So this green color mainly due to this particular mineral. So here, so if you consider so usually this green color that is available, chromium can substitute, replacing aluminium in jadeite structure, minor amount of, trace amount of chromium substitution that yield this beautiful green color. So here, jadeite bearing rocks, jadeite bearing rocks, they mainly produce under specific metamorphic condition, because this particular mineral that is stable under relatively high pressure conditions. Without high pressure conditions, jadeite cannot produce. So this is a very common reaction that describes this a metamorphic reaction. So during metamorphism, so metamorphism actually we can classify as a regional scale metamorphism or contact metamorphism. So regional scale metamorphism can take place during continental collision, during subduction. So here this illustrates subduction zone. So during subduction, the series of metamorphic rocks can produce. So here zeolite phases, green schist phases, blue schist. These are high pressure rocks. Eclogite. So jadeite, they produce mainly in blue schist and towards this eclogite phases rock. So this is one of the common metamorphic transformation, solid state transformation. Actually, this particular sodium rich plagioclase feldspar under high pressure conditions, this albite that is not stable, albite breakdown producing jadeite and quartz. So then under the enrichment of this jadeite, the particular rock would appear under green color. We call it as jade. So then garnet. It's a very common mineral in most of the metamorphic rocks. In green schist, amphibolite, granulite phases rocks. It's a common rock form in mineral. But so frequently if you observe garnet under the microscope, you can identify different inclusion phases. So these inclusions like quartz inclusion or other mica inclusion, they may affect negatively on this the color of this garnet, and sometimes most of the garnet contain high amount of fractures. That is also negative effect, but there is a possibility a coarse grain garnet can produce very transparent, limited amount of fractures would available and limited amount of inclusions may available. So then they can use as gems, a gemstone. So after weathering of this rock, this garnet is survive under weathering condition up to some extent, so they can deposit somewhere else from its particular rock, host rock. So then we can mine those garnet-rich gravel. So it's sometimes a secondary deposit. So during mining, you can identify some of the garnet, they are very clear. It means transparent, fracture-free, inclusions-free. So then we can use them as there's an economic value. We can cut and polish it. So another two minerals, they mainly form during regional scale metamorphism, like continental collision, especially tanzanite. It's a zoisite group mineral, but due to incorporation of vanadium into its structure, it has this beautiful blue color. Saurite, that is also a type of garnet, grossular garnet. It means calcium-rich garnet, but due to incorporation of chromium or vanadium in minor or trace amount, that yield this beautiful green color. So they are mainly produced, these minerals mainly produced during metamorphism. In metamorphic rocks, there is a possibility the formation of gem quality, this zoisite. Then gemologists, they call it as tanzanite. So due to incorporation of minor or trace amount of chromium or vanadium into common rosiular garnet, calcium-rich garnet, that provide this beautiful color. If it is a relatively coarse grain and if it is inclusions free and it is fracture free, then it has an economic value. And final part, only last 2 or 3 slides. So metamorphic corundum deposit, gem deposit, actually gem corundum. So corundum means that is only aluminium oxide, but just aluminium oxide, sometimes it is colorless. There is no any economic value other than it can, due to its high hardness, we can use it as an abrasive material to grind some of the materials. But due to incorporation of different trace elements like chromium or iron or titanium, that result this beautiful color. So when you are considering the most of the metamorphic rocks associated gem deposit, they mainly produce in regional scale metamorphism like continental collision in upper, so most probably amphibolite to granulite phases condition, sometimes metasomatic process, sometimes in marble, for an example, in a metamorphic terrain, they can interact with hydrothermal fluid, aluminium rich fluid. So then corundum can produce. So when you're considering the distribution of this gem quality corundum in Earth, we can identify 2 main orogenic events. Orogenic events mean mountain building processes that happen through the Earth history. So first one is when you are considering the gem deposit, they are available in Sri Lanka, southern part of India, and southern part of Madagascar, and eastern part of Africa. They share very similar, many similarities. The available inclusions and this metamorphic grade of the surrounding rocks. So likewise, so the reason was, so they produce the particular rocks, so particular gems bearing rocks produce during this particular time period, most probably 600 to 550 million years ago, during amalgamation, during formation of this supercontinent, Gondwana. During that, this east and west Gondwana collided, producing a mountain belt here. So Sri Lanka, this southern part of India, southern part of Madagascar, eastern part of Africa, it's a continued mountain belt during that time. So now, most of the rubies and sapphire bearing corundum deposit, we can identify in these countries. So if you dated them, they mainly lies ages around 550, 500, like that, those rocks, those regions. In addition to that, in Asia, especially in this part, associated with the Himalayan mountain belt, there are some rubies, rich metamorphic gem deposits are recorded, especially countries around, actually, like in Afghanistan, Tajikistan, Pakistan, then Nepal, and after that, Vietnam, Myanmar, likewise. So this is responsible for relatively younger orogenic event, Himalayan orogenic. So those in Himalayan orogeny, those deposit mainly rich, these rubies associated with first marble. So after dating of those rocks, the researchers got these ages. So it's a post-tectonic events after formation of this mountain. So some of the post-tectonic events were going on. So during that, these ages suggested these deposits were produced. So these are some examples for gem quality corundum deposit. In the world, mainly, we can identify rubies, very valuable, beautiful corundums. They are associated with, they produce mainly during these 2 orogenic events. So these orogenic events mean they are continental collisional event. Final product is formation of mountains and metamorphic rocks. So now this corundum also produced during this metamorphism. Yes, that's the content for my lecture. So I mainly target to introduce gemstone and why, some facts, some reasons to explain why are gemstone rare, and then some of the examples, especially origin of gemstone in some igneous rocks like pegmatite, and some of the igneous rocks can serve as transporting agent to transport some of the produced gems like diamond. That example was kimberlite, and some of the metamorphic origin related gem deposit. So that's the available part. So thank you very much. Now, if you have questions, now that's the time.
Thank you, Dr. Dharmapriya, for the informative lecture on gemstones. There is one question in the chat. Can you check?
Okay, I will check. Yeah, sedimentary origin. So her question was some examples for sedimentary related gemstone. Actually, first I mentioned that geoids. So geoids, that's also type of sedimentary origin, because I will go to that particular slide first. One example here. So initially the required free space that is produced through the volcanic process. Sometimes this surrounding rock, that is basalt. So here, because sometimes basalt may contain dissolved gases, during escaping of these gases, some large scale gas bubbles initially created within these rocks. So then after some time, these gas spaces can escape from that. Initially gas was available. So during fracturing, this gas can release. So then through those fractures, groundwater can reach us. Sometimes there is a possibility this water, sometimes hydrothermal fluid, not only groundwater. Hydrothermal fluid means those are hot fluids contain dissolved iron. Sometimes those hydrothermal fluid, they are rich with silica, sometimes calcium. Its composition varies. If silica rich hydrothermal fluid, if it's reached to this cavity, then quartz can precipitate silicon dioxide. But amethyst mean, to result this color, iron, ferric iron should incorporate as an impurity. So it is a different phenomenon actually. This then this ferric iron, under the presence of radiation, it will convert into Fe4 plus. So likewise, it's a different mechanism for formation of the color in amethyst. But because basalt, it's an iron rich rock. So there is a possibility in this environment, in addition to silica and oxygen, iron can also available as a minor element. So then in this crystallized quartz, and due to incorporation of ferrite into its structure, so this is the final result. So that is one of the examples. And another one, yes, how do scientists test the models of gemstone formation, considering the gemstone are rare? The indirect laboratory method prepared actually. So nowadays, so this investigation of these gemstones, people mostly use, sometimes they inversely study. For an example, you may identify, you can collect a gemstone from an alluvial deposit. It's sometimes a very big sapphire or ruby. So if you need to study about its origin, we have to consider various factors. Sometimes we can, because you cannot destroy it. If it is a gem, you have to use non-destructive methods for testing. If you need to study its origin, sometimes we have to get information related to its chemistry. Most of the occasion, this way is use non-destructive method. So sometimes it is impossible, because if you need to analyze the trace element and major element, sometimes you have to use XRF or less ICP-MS, then small portion of the particular gem may damage. But in addition to that, non-destructive methods such as Raman different spectroscopic method people use. And then after analyzing the available trace element data, so that's one of the best. And sometimes after studying of inclusion phases, so then we can get an idea after discriminating those information with already published materials, we can get an idea. Okay, these gems mainly produce during metamorphism. So this is during magma crystallization. So likewise, even in laboratory scale, people use mainly, actually people produce synthetic gems. So that is also a huge in gem industry. So especially even experienced gemologists, sometimes they face some difficulties to distinguish natural gems and synthetic gems, because natural gem has very high value, but synthetic gems, very similar, the appearance. So sometimes people use the availability of inclusions, because during formation of natural gems, most of the occasion, different air or gas or sometimes other mineral inclusions may incorporate the structure. But during synthetic gem production at laboratory scale, so they are most of the occasion they are inclusions free. So those features people use. Studying of origin of gems, it's a challenging task, because these gemstones are very rare in the nature. And although if you extract gems, because you cannot break them, you cannot prepare a thin section to study inclusion phases. So very carefully you have to handle this. It's a challenging task. Sometimes people use different modeling techniques. So laboratory techniques mainly people use to produce synthetic gems.
Okay, I think there are no more questions.
I will send this presentation to you, Adira, then you can circulate it among the student.
Okay, sure.
Okay, thank you very much for inviting me for this lecture, and thank you very much for all the participants. So have a nice day.